right, so Chapter 8 is an introduction to hypothesis testing. So the logic of hypothesis testing is that it's the most commonly used method for measuring inferential procedures. So if we had to define the logic of hypothesis testing, we could say that it's a statistical method that uses sample data to evaluate a hypothesis about a population. So when it comes to how we engage in hypothesis testing, we first state a hypothesis about a population. Then we describe the expected characteristics of the sample based on that hypothesis. We obtain a random sample from the population and compare the obtained sample data with the prediction that was made from the hypothesis. If it's consistent, the hypothesis is reasonable. If there's a large discrepancy, the hypothesis is rejected. So if we take a look at figure 8.1, the basic research situation for hypothesis testing is shown here. We've got a population parameter, which is known or assumed before the study. And the purpose of the study is to determine whether the treatment has an effect on the population. And if we look at figure 8.2, we can see from the point of view of the hypothesis test, the entire population receives the treatment, and then a sample is selected from that treated population. In the actual research study, however, a sample is selected from the original population, and the treatment is administered to the sample from either perspective. The result of that is a treated sample that represents that treated population. So there are 4 steps that are involved in hypothesis testing. The first thing we want to do is state a hypothesis, then set the criteria for making a decision, collect data, and compute those sample statistics, and then we make the decision. So when we want to state the hypothesis, we have to look at the null hypothesis, which states that the treatment has no effect, there's no change, there's no difference or no relationship between the independent variable and its effect on the dependent variable. And then the alternative hypothesis is that there is change, there is a difference, or there is a relationship that exists between those 2 variables. In step 2, we can set the criteria for a decision. You have a distribution of sample means that can be divided into 2 sections, and alpha level is the level of significance, which will tell us the probability value that's used to define the concept of very likely in a hypothesis test. Also in step 2, you've got critical regions that consist of extreme sample values that are very unlikely or to be obtained if the null hypothesis is true. And then you've also got boundaries for the critical regions, which are determined by the probability set by the alpha level. If the sample data fall in the critical region, the null hypothesis is then rejected. So if we take a look here at figure 8.3, we've got the set of potential samples, and it's divided into those that are likely to be obtained and those that are very unlikely to be obtained if the null hypothesis is true. And then in 8.4, we can see the critical region, the very unlikely outcomes for alpha, which is 0.05. So if we do a little learning check here, we can see that a sports coach is investigating the impact of a new training method. In words, what would the null hypothesis say? Is it A, B, C, or D? I'll give you a few moments to think of what might be the correct answer. And hopefully you came up with answer B. The new training program produces results similar to the existing one, because that is what the null hypothesis says, is that there's no change. Here's 2 more true-false questions. If the alpha level is decreased, the size of the critical region decreases, and the critical region defines unlikely values if the null hypothesis is true. Give you a few moments to think about those answer choices. And for both of them, they are true. Alpha is the proportion of the area in the critical regions, and that is the definition of what a critical region is. And then for step 3, that is when you collect data and you compute those sample statistics. The data are going to always be collected after the hypothesis is stated. The data are always going to be collected after establishing the criteria for the decision. And this sequence assures objectivity and an honest, objective evaluation of the data that's obtained. And also during step 3, that's when you compute a sample statistic like a z-score to know the exact position of the sample. So z is the difference between the observed sample mean and the hypothesized population mean. That's then divided by the standard error of the mean. And then in step 4, you're going to make a decision. And that's when the obtained z-score value is used to make a decision of 2 possible outcomes. You have the sample data, which are located in the critical region, and we have to decide, are we going to reject the null hypothesis? And the sample data that's not located in the critical region, that means the data does not provide strong evidence that the null hypothesis is wrong. So then we will fail to reject the null hypothesis. So an analogy for hypothesis testing is that the null hypothesis is either rejected or the researcher fails to reject the null hypothesis. The process for conducting a hypothesis test is very similar to like a jury trial. The jury begins with the null hypothesis that the person is innocent until proven guilty. And then police and the prosecutor have to gather evidence, data, to test whether the accused really committed the crime. With sufficient evidence against the defendant, the jury will reject the null hypothesis and define that the defendant is guilty. With insufficient evidence, the defendant, the jury is going to fail to find the defendant guilty, because there's not enough evidence, so they won't be able to conclude that the defendant, they're going to say not guilty, although they can't conclude that the defendant is indeed innocent. It wasn't proven. If we take a closer look at the z-score statistic, the z-score is like a ratio. It's the actual difference between the sample mean and the hypothesized population mean. It can be divided by the standard error. And when we have those z-scores, and if it's +3, that means the obtained difference is 3 times larger than would be expected if the treatment had no effect. So here's a second learning check. True, false. When the z-score is quite extreme, it shows that the null hypothesis is true. Or true, false. A decision to retain the null hypothesis means that you prove the treatment has no effect. I'll give you a few moments to think about the correct answer. And for both of those, they're both false. An extreme z-score is in the critical region. This is very unlikely if HO is true. And then we would fail to reject the null hypothesis because it doesn't prove that it's true. There's not enough evidence to reject that hypothesis. So sometimes we also can have something called uncertainty and errors in the hypothesis testing. Hypothesis testing is a type of inferential process. It uses limited information from a sample to make a statistical decision, which is then used to make a general conclusion. You'll have that sample data, which is used to make a statistical decision, which allows us to make an inference and draw a conclusion about a population. But sometimes errors can indeed be possible. So a type 1 error occurs when a researcher rejects a null hypothesis that is actually true. It's an error. So the researcher concludes that a treatment has had an effect when it really hasn't. So the alpha level is the probability that a test will lead to a type 1 error. It determines the probability of obtaining a sample data in the critical region, even though the null hypothesis is true. So it tells us the measure of error. And a type 2 error occurs when a researcher fails to reject a null hypothesis that is actually false. So they fail to detect a real treatment effect. That means your sample mean is not in the critical region, even though the treatment has an effect on the sample. So those type 2 errors are usually not easily identifiable if they're there. Then we have table 8.1, which tells us some possible outcomes for a statistical decision. And figure 8.5 tells us the location of those critical region boundaries for 3 different levels of significance. for 0.05, 0.01, and 0.001. So if we did another learning check here, true, false, a type 1 error is like convicting an innocent person in a jury trial, and a type 2 error is like convicting a guilty person in a jury trial. I'll give you a few moments to think about that. So the first one is true. Innocence is the null hypothesis for the jury trial. The conviction is like rejecting that hypothesis. But the second one is false. When we convict a guilty person, that's not an error. But acquitting a guilty person would be a type 2 error. So to summarize, these are the 4 steps we're going to go through when we're trying to make a hypothesis. First, we're going to state the hypothesis and select the alpha level. Then we're going to locate the critical region, compute the test statistic, and then make a probability-based decision about the null hypothesis. When it comes to reporting the results, a result is significant or statistically significant if it is very unlikely to occur when the null hypothesis is true. In APA format, you have to report that you found a significant effect, report the value of the test statistic, and report the p-value of the test statistic. There are a few factors that can influence a hypothesis test. You could look at the size of the difference between the sample mean and the original population mean. If there's a larger discrepancy, then you have a larger z-score. You can also look at the variability of the scores. If there's more variability, then there's a larger standard error. The number of scores in the sample can also indicate if it's a larger N number than a smaller standard of error. We can also make some assumptions regarding random sampling, independent observations, the value of what's being unchanged when it comes to our standard deviation. The normal sampling distribution could also be an assumption we make. So here's another learning check. A researcher uses a hypothesis test to evaluate and which combination of factors is most likely to result in rejecting the null hypothesis. So in this case, I hope you thought of the answer as being B. Here's a couple more learning checks. An effect that exists is more likely to be detected if the number of the sample size is large, or an effect that exists is less likely to be detected if the standard deviation is large. Is that true or false? And both of those are true. A large sample produces a smaller standard error and a larger z-score, and a larger standard deviation increases the standard error and produces a smaller z-score. When it comes to the direction of our hypothesis test, the tail typically tells the tale. So the standard hypothesis testing procedure is called a two-tail non-directional test because the critical region is divided between the two tails of the distribution. However, sometimes the researcher has a specific prediction about the direction of the treatment. When that specific direction of the treatment can be predicted, it can be incorporated into the hypothesis. So in a one-directional hypothesis test, the researcher is going to specify either an increase or decrease in the population mean as a consequence of treatment. So here's an example of that, the critical region, for example, 8.3. And then in a two-tailed test, it's going to require a relatively large difference regarding the direction, whereas a one-tailed test allows for rejecting the null hypothesis when there is a relatively small difference in the specified direction. In two-tailed tests, there should be these things should be used unless there's a strong justification for a directional prediction. So let's go ahead and try another learning check with a researcher who's predicting that a treatment will decrease scores. If this treatment is evaluated using a directional hypothesis test, then the critical region for the test is A, B, C, or D. Take a moment and think about the correct answer. And hopefully you came up with B. Would be entirely in the left hand tail of the distribution. So when it comes to hypothesis testing and we're looking at effect size, some scientists are concerned about hypothesis testing. They focus, when the focus of the test is on data and not the hypothesis. Significant effects are not always substantial. So those effect size measures are going to look at the absolute magnitude of the treatment effect and the independent nature of the sample size. Cohen's d can help measure the effect size simply and directly in a standardized way. So here's a formula for how we can look at Cohen's d and measure the effect size. That's in your book. And if we look here at figure 8.7, we can see the appearance of a 15-point treatment effect in two different situations. In part A, we've got the standard deviation that's 100 and a 15-point effect that's relatively small. And then in part B, we have the standard deviation of 15 and a 15-point effect, which is relatively large. So Cohen's d can use the standard deviation to help measure the effect size. So here's another learning check, true or false. Increasing the sample size will also increase the effect size, and larger differences between the sample and population mean increase effect size. Take a few moments and think about the correct answer. And we have false, sample size did not affect Cohen's d. And true, the mean difference is in the numerator of Cohen's d. Statistical power is the power of a statistical test and the probability that the test will correctly reject a null hypothesis. It will help detect a treatment effect if one actually exists. And power usually is estimated before starting a study, but requires several assumptions about factors that influence power to be made. So in order to calculate power, we're going to follow these three steps. First, we're going to sketch the distribution for the null and alternative hypothesis. Then we're going to locate those critical regions and compute the critical scores. And then we're going to compute those z-scores for the alternative as well. Here's a distribution in figure 8.8 that shows how we can measure power for a hypothesis test. The distribution on the left, that's the distribution of a sample means that would be expected if the null hypothesis were true. For the null distribution, the expected value is 80. The critical region is defined for this distribution as well. You've got on the right-hand side, it shows that the distribution of sample means that would be obtained if there was an 8-point treatment effect, with the expected value of the distribution being 88. So you can see in that shaded area on the right, it gives the power of the hypothesis test. Notice that if it were there would be an 8-point effect. Roughly 1/3 of the sample means would be in that critical region. So if we want to increase power, we can look at as the sample effect size increases, so does the power. A larger sample size will produce greater power. And using a one-tailed directional test is also going to increase the power relative to a two-tailed test. If we want to decrease the power, we need to reduce our alpha level to reduce the power, or use a two-tailed non-directional test. And then figure 8.9 shows us a demonstration of how the sample size affects power for a hypothesis test. The left-hand side shows the distribution of sample means that would occur if the null hypothesis were true. The critical region is defined for this distribution. The right-hand side shows the distribution of sample means that would be obtained if there were an 8-point treatment effect. Notice that nearly all of the alternative distribution is shaded. Thus, increasing the sample size to 25 has increased the power to nearly 100% compared to nearly 36% of the sample size, with 4 being the number necessary. And then in 8.1, we've got the null and alternative distributions for a 16-point effect when we've got a sample of 4 and a standard deviation, when our alpha is 0.05 for two tails compared to 8.6, which had a 16-point effect and 89.25% probability, which is much larger than the 8-point effect, with the power being 35%. Then also in figure 8.11, we've got the distributions for a power analysis when the researcher assumes that the treatment will cause a 20-point decrease. The null distribution is on the right-hand side and the alternative distribution is on the left-hand side. So let's do another couple of learning checks here. The power of a statistical test is the probability of blank the null hypothesis. What would be the correct answer? So the power tells us the probability of C, rejecting that null hypothesis. And then here's another true-false question. Cohen's d is used because alone a hypothesis test does not measure the size of a treatment effect, and lowering the alpha level from 0.5 to 0.01 will increase the power of the test. Take a few moments and think about those correct answers. And the first one is true. The differences might be significant, but not of a substantial size. And the second one is false. It is less likely that the null hypothesis will be rejected with a small alpha. I hope all of this has helped you guys understand the information in Chapter 8.